In this lecture, we are going to see about diversity combining techniques. Before entering into the topic, we'll see what is meant by diversity. Diversity is actually one of the techniques which is used to improve the received signal quality. The principle behind diversity involves transmitting multiple copies of a signal in a different paths, or we can say in different branches. Usually what we will do, we will transmit single copy of a signal from a transmitter and the same will be received at the receiver side. But in diversity, in spite of transmitting single copy of a signal, we are going to transmit multiple copies. This diversity technique can be applied either at the transmitter side or at the receiver side. If it is applied at the transmitter side, it is called transmit diversity, or if it is applied at the receiver side, it is called receiver diversity. For applying diversity technique, we need multiple antennas. In the next point, the signal propagating through different paths will have different signal to noise ratio. This is because as the signal propagates through different paths, each path will have different fading characteristics. Some signal will have deep fading effects, whereas some other signal will not have deep fading effects. So depending upon the fading effect, the signal to noise ratio may vary. And the key point here is the paths through which the signal propagates must be highly uncorrelated. The next one is types of diversity. The first one is microdiversity. Microdiversity is used to overcome the effects of small scale fading. The most 5 common methods of microdiversity are: the first one is spatial diversity. Here several antennas are used at the receiver side and these antennas must be properly separated. Second one is temporal diversity. It involves transmission of signals at different times. Third one is frequency diversity. It involves transmission of signals at different frequencies. Fourth one, polarization diversity. In polarization diversity, multiple antennas with different polarization is used. That is, the antennas can be either horizontally polarized or vertically polarized. And the last one is angular diversity. In angular diversity, multiple antennas with the different antenna patterns is being used. So this is about microdiversity. And the next one is macrodiversity. Macrodiversity is used to overcome the effects of large scale fading. So here is our topic, diversity combining techniques. What is diversity combining techniques? So we have already seen we are going to transmit multiple copies of multiple copies of a signal at the transmitter. So how the signal must be chosen at the receiver side? So this is being done with the help of diversity combining techniques. The first one is selection diversity. So this is the block diagram of a selection diversity. You can see it has M diversity branches, that is 1, 2 and goes up to M. It has a M demodulators whose gains are variable, that is you can vary these gains so as to provide same average SNR for each branch. The principle behind this selection diversity is all the branches are scanned simultaneously at the same time. So all the branches are here scanned simultaneously at the same time, and the branch which is having highest instantaneous SNR is being chosen. So that is what given here. The branch which is having high SNR is selected. So this is the principle behind selection diversity. This selection diversity is the simplest technique. And the next one is feedback or a scanning diversity. This is somewhat similar to selection diversity, but here the signals are scanned in a fixed sequence, whereas in selection diversity, the signals are scanned simultaneously. Here, the signals are scanned in a fixed sequence. So let's go to the block diagram. It consists of a comparator. This comparator has a preset threshold SNR. So this comparator will compare this threshold SNR with the received signal SNR value. Whenever the received signal SNR value is greater than the threshold, then that signal will be chosen. So this is the feedback or a scanning diversity. So next point, what will happen if the SNR value falls? If the SNR value falls, the scanning process must be initiated from the beginning. The disadvantage of the feedback or scanning diversity is it takes more time than the selection diversity, because in selection diversity we'll be scanning simultaneously all the signal, but in feedback diversity the scanning is done in a fixed sequence, so it will be definitely a time consuming process. But the advantage is it is simple to implement because it needs only one receiver at the receiving end. The next one is maximal ratio combining diversity, or shortly called as MRC. This is the block diagram of MRC technique. You can see it has M diversity branches. This gamma 1, gamma 2, gamma M are the individual SNR branches, individual SNR value of each branches. And this gamma M is the summation of all the individual SNR. So let's see what happens here. Here we have something a feedback like structure called adaptive control. So with the help of this feedback, we can able to weight the signals of each branches. How? Let's see. For example, consider the signal to noise ratio of the first branch is very low. So I can boost up this with the help of this adaptive control. So whenever the SNR value of a particular branch goes low, I can vary this adaptive control so that I can vary the gain here. So by varying the gain here, I can boost up the signal to noise ratio of a particular branch. So by doing this, we can boost up the signal to noise ratio of any branch here. After this, all of the individual SNR value is being summed up here. So this gamma capital M is nothing but the sum of individual SNR. This gamma M will always be greater than the threshold value, because it is not an individual value, it is actually summation of all the individual SNR values. So at any time this gamma M will always be greater than the threshold value. We can see some block which is called a co-phase. So what is the purpose of the co-phase? As the signal travels through the multiple paths, definitely there will be phase deviation. So in order to make all the signal to be in phase, we have this block which is called co-phase. This MRC technique is best of all other techniques, and it is being usually used in the digital receivers. And so here in MRC, thereby by varying this adaptive control, we can able to vary this individual signal to noise ratio with the help of varying this gain. So this is the principle behind maximal ratio combining diversity. And the last one is equal gain combining technique. This equal gain combining technique is somewhat similar to MRC technique. But here, what is the difference is the weights of all the branches are all set to unity. So let's see the block diagram of MRC. So this is actually the feedback control. So let us consider what will happen if the feedback goes wrong. Not all the cases, there is a possibility that the feedback control might go wrong. So what will happen if the feedback goes wrong? If the feedback goes wrong, it will lead to improper weighting of the signals in each branches. What will happen if the weighting is improper? Then the complete system will be a failure. So in order to overcome this drawback of maximal ratio combining diversity, so that is MRC technique, we have equal gain combining technique. So what happens here, in spite of varying the weights, here all the weights of the branches are set to unity. So that is the only difference between the equal gain combining technique and the MRC technique. Apart from this, all other things are same. So here the signals are co-phased and then summed. So this block is same. Let's see the performance of this equal gain combining technique. This performance of the equal gain combining technique is marginally inferior to MRC. That is, it is moreover close to the performance of MRC technique, but it is more superior to selection diversity. That is, it is best than the selection diversity. So this is about diversity combining techniques. Thank you.